Hi everyone. Today we will start Unit 2, that is the development of adaptive filter theory and searching the performance surface. And this second unit is divided into two parts. First part is development of adaptive filter theory and second part is searching the performance surface. First we'll start with the first part, that is development of adaptive filter theory. In that, the first topic is introduction to filtering. What is this filtering problem? The term estimator or filter is commonly used to refer to a system that is designed to extract information about a prescribed quantity of interest from noisy data. Here, the filter is mainly which refers to a system which is designed to extract information about a prescribed quantity of interest from noisy data. We have to extract the information. That is what the purpose of this filter. With such a broad aim, estimation theory finds application in many diverse fields like communications, radar, sonar, navigation, seismology, biomedical engineering, and financial engineering, among others. Consider, for example, a digital communication system, the basic form of which consists of a transmitter, channel, and a receiver connected together, which is shown in figure 1. This is an example of digital communication system, block diagram of a communication system. Digital communication system, which consists transmitter, channel, and receiver. Here, the function of transmitter is to convert a message signal. Is the function of a transmitter is to convert a message signal which consisting of a sequence of symbols, ones and zeros, generated by a digital source. For example, like computer generated the signal into a waveform suitable for transmission over the channel. Okay, now typically the channel suffers from two major kinds of impairments. This channel suffers from two major kinds of impairments. First one is intersymbol interference and the second one is noise. First, intersymbol interference. Ideally, the impulse response of a linear transmission medium is defined as h of t equals to a delta t minus tau. This is equation number 1. And equivalently, we may characterize in the frequency domain by writing h of j omega equal to a exponential function of minus j e to the power of minus j omega tau. Here, this intersymbol interference is actually, we have to reduce this intersymbol interference. Here in this equation, this is the first equation, h of t equals to a delta t minus tau. Here t denotes the small t continuous time, this one, and h of t designates the impulse response. This is the impulse response of linear transmission medium where small t denotes the continuous time, and A is capital A is an amplitude scaling factor, and this of t delta of t is simply it's a Dirac delta function. Delta of t is a Dirac delta function or simply unit impulse function, and denotes tau denotes the propagation delay incurred in the course of transmitting the signal over the channel. This tau is simply which denotes the propagation delay incurred in the course of transmitting the signal over the channel. This is the equation 1 in time domain description of an ideal transmission medium. The equivalent for this equation 1 is this one. That means simply we have converted from time domain to frequency domain. H of j omega equals to a exponential function minus j omega term, where here j is the square root of minus 1, and this omega denotes the angular frequency. H of j omega is the frequency response. H of j omega is the frequency response of the transmission medium, and this exponential function. This is, in practice, it is impossible for any physical channel to satisfy the stringent, difficult requirements, tough requirements embodied in the idealized time domain description or in the frequency domain also. Here, what we will do is simply the best that we can do is to approximate this equation 2. Here, the best thing here we can do is to approximate this equation 2 over a band of frequencies representing the essential spectral content of the transmitted signal, which makes a physical channel dispersive. In digital communication system, this channel impairments, two impairments are there. Intersymbol interference is the first one, second one is the noise. The first one we are talking intersymbol interference. Here, this channel impairment in digital communication system gives rise to this intersymbol interference. It's the second one is a noise. Some form of noise is present at the output of every communication channel. Some form of noise is present at the output of every communication channel. The noise can be internal to the system, as in the case of thermal noise, generated by an amplifier at the front end of the receiver, or external to the system due to interfering signals originating from the other sources. The noise may be internal or it may be external. Internal, for example, thermal noise, which will be generated an amplifier at the front end of the receiver due to the agitation of electronics, and it may be external noise. Different types of noises are there, external noises. Now, the net result of these two impairments, intersymbol interference and noise, is that the signal received at the channel output is a noisy and distorted version of the signal that is transmitted, right? The result of this is at the output end of the receiver, what we'll get the noisy and distorted version of the signal which is transmitted, right? The function of the receiver is to simply, now the function of the receiver is to operate on the received signal and deliver a reliable estimate of the original message signal to a user at the output of the system. Now, this is another example. First example is the digital communication system. Second example is a block diagram depicting the components involved in the state estimation, namely x cap of t. This is another example involving in the use of filter theory, right? Now, here consider the situation which shows a continuous time dynamic system whose state at time t is denoted by the multi-dimensional vector x of t. Here, this is figure 2 shows a continuous time dynamic system whose state at time t is denoted by the multi-dimensional vector x of t. The equation describing the evaluation of the state x of t is generally subjected to system errors. The filtering problem is complicated by the fact that x of t is hidden, and the only way it can be observed is through the indirect measurements whose equation is a function of the state x of t itself. Here, moreover, the measurement equation is subjected to unavoidable noise of its own. Here, the dynamic system, it may be an aircraft in flight or it may be something else. Here, The estimation theory, which illustrates here by the two examples. First one is the digital communication system, and second one is the continuous time system. Simply here, for example, if this we consider it as a the aircraft system, aircraft in flight, or simply aircraft, in which case the position and velocity of the aircraft constitute the element of state x of t, right? Here this one, and the measurement system may be tracking radar in any event given the observable y of t observations produced by the measuring system over the interval 0 comma t, and given prior information the requirement is to estimate the state of exam this x cap of t of the dynamic system. Here this entire system we are assuming it as aircraft. Here the velocity, position and everything will be considered and comes under state x of t, and the measuring the different parameters by using radar system comes under measuring system, and we'll make some observation, and finally we'll estimate the state, and which will be denoted by the x cap of t. This is the simple operation of this continuous time system. Now the next topic is three basic kinds of estimation. Now here estimation plays an important role in adaptive filter theory. So here we have to learn three basic kinds of estimations. Three basic kinds of estimations are: the first one is the processing operations are the three basic kinds of information processing operations are filtering, smoothing and prediction, each of which may be performed by an estimator. These are the three information processing operations. First one, A is the filtering, B is the smoothing, and C is the prediction. And each of these may be performed by an estimator. Now we'll see one by one. The filtering. Filtering is an operation that involves the extraction of information about a quantity of interest at a time t by using data measured up to and including t. Next, the smoothing operation. It's simple as in a posteriori, after the fact form of estimation, and that data measured after the time of interest are used in the estimation. Filtering is simply an operation which involves the extraction of information which is of interest by this noisy data. We have to extract the information, whereas smoothing information is a posteriori, after the fact the information will be utilized and the data measured after the time of interest are used in the estimation. After data is used in the process of information, that is the smoothing process. Then the prediction. Here it's simply the forecasting side of estimation. It's aimed to derive information about what the quantity of interest will be like at some time t plus tau in the future by using data measured up to and including time t. This is prediction. We have to forecast the values which we are going to estimate. These are the three basic kinds of estimations are there. Then the next topic is linear optimum filters. Up to this is one part. This is the simple. Here we are trying to developing the adaptive filter theory. In the process, in that process, first we have to learn the fundamentals like filtering, smoothing, and the third one is the prediction. That means these are the three basic fundamentals we must know. Next topic is linear optimum filters. In next lecture, we will study this linear optimum filters. Thank you.